MEG-based Brain Geminoid Interface.
Yes, thank you very much. So, good morning everyone, and thank you very much for having me here. So I'm going today maybe to talk about something that looks like completely different, but it's almost the same things. You have been talking about robots, but I'm going to talk about human. But I will make that connection between human and robot. So today I'm going to talk or present like decoding of simultaneous bilateral hand movement, okay? For controlling human-like robot, we call it Geminoid. Okay, and this is the idea is to increase like the dimensionality. We are talking about degree of freedom, dimension of control. Okay, and we want to achieve some continuous and multi-dimensional brain-machine interface. So we want to make a human able to do many things. Okay, I will do my best like in the first to define the problem and its impact on the society and how we are thinking to solve this problem. And then in the end, I will show you like real-time video demonstration about like controlling a human-like robot using only your brain waves. Okay, so like everywhere, as you know, like young people, I'm sorry to say that, but it's true. Young people, they bring a new idea and energy to any workplace. But yeah, I mean, they have to work over time to achieve many things in their life. So after working many hours, they become exhausted, stressed, inefficient, and some of them, especially maybe in Japan, may suffer from stroke or heart attack from working too much. So our idea, we want to increase the ability of multitasking. And like that, we can keep the productivity the same, and we can increase like his multitasking ability, but we can decrease like over time. So what we want to do, we do believe, like scientifically speaking, that the brain is able to control more than one or two hands or two arms. So we can do that. And that's our idea. We want people to be able like to do many tasks in the same time. So that's what we were looking for. And this one can increase like the neuroplasticity in the human. So the neuroplastic benefits. Okay, so anyway, many researchers maybe have been trying or dreaming to like add more additional arm to our body. But most of them, they have been trying to control these extra devices using muscles activity or like some mechanical aspect. None of them had tried before to use like brain activity, which like the most like natural way and more convenience for daily life applications. So I do believe like it's our job to do this kind of things. So I'm not sure if most of you are familiar with brain-machine interface or brain-computer interface, but anyway, there is here like brief definition about like BMI-based motor imagery. So it's very simple. So we decode some signals from the brain, and then we use some machine learning for classification or regression or for decoding, and then we will get some commands. And we usually use some neurofeedback. So like all previous works have been trying to decode unilateral hand movement. Like for example, left hand or right hand. So our goal is to increase the dimensionality, the degree of freedom. We want like this BMI, we want a human to be able to control many degree of freedom. So that's why like before controlling additional hand, we call it like the third arm, we have to control bilateral hand movement. So we don't really know what is going on inside the brain when someone is moving his like bilateral hand. Like all studies, they have been like successfully like explaining and doing everything using unilateral hand. So that's it's done. But our goal is to clarify like the neural mechanism and what is going on inside the brain when someone is like doing multitask process. And we have like two, to be honest with you, like we have two purpose. One of them, like engineering purpose, it's just like to control a human-like robot. So you can see this one, it's like a very famous TV star in Japan. And all these kind of robots are made by Professor Hiroshi Ishiguro. I have been working with him in this project. So our goal was like to control using MEG equipment. This MEG equipment is just for recording the brain waves. And then we made some algorithm to decode what is going on and analyze this kind of like brain activity, and then send the command to the robot, human-like robot, we call it Geminoid, and we see in real time what is going on. But for like neuroscientific point of view, we want to increase human ability of multitasking. That's the most important in the sensory motor area. Okay, so that's why we propose like a new experimental paradigm, and we ask the subject like to do bilateral hand movements and to follow like this paradigm, and this is very important for us to record the brain waves. And then we of course do more like source and sensor level analysis. What I mean about that we do a lot of like time frequency representation. So as you can see here, for example, if someone is grasping his hand, so you can see this red signal of your inside your brain. So we try to decode this kind of signals. So I will try to talk a little bit in detail. So for example, when you grasp your hand, we have like here frequency bands. Okay, let's talk about from 0 to 100. We have like alpha, beta, and high gamma. So you can see that there is kind of power decrease here in the alpha and beta bound. And then you can see here like the post movement, this is after 0.5 seconds. So you can see like beta rebound. So there is like increasing in the power, okay? And here in the high gamma band, we have like increasing in the power. So this is like the most like standard like brain waves when someone grasps his hand. Okay, and we do some things like to find which like the most relevant like sensors around the brain. This is also very important. Okay, and then we check using like source level analysis and sensor level analysis. I will talk about sensor level analysis. So here you can see like someone when he's moving his hand, so it's completely different if you are, for example, opening this one and closing this one. So you can see like kind of bilateral activation, and that's our job, like to distinguish between these 4 types of movements. Okay, and we do like more statistical analysis to calculate, for example, a value to understand if it's this one, if it's significant enough, like across here we use like 10 subjects, and we can see, we still see like bilateral activation when someone is moving his hand, bilateral movement, okay? So, I'm doing my best not to go in details, but okay, this is like also for each sensor, you can see like this typical like kind of time frequency representation. When someone, I told you, grasp his hand, so there is like power decrease in the alpha and beta, and then the power increase in beta again. So you can see it here around the bilateral movement. So hemispheres. So we check that for like real movement when someone performed the movement, and in the same time when someone imagined the movement. So we need like imagination, and we need also like motor execution. We call this one motor execution, and this one, for example, motor imagery. And then we classify or distinguish among like 4 classes of bilateral movement. And we use like kind of simple algorithm, except here we use TSSS methods to distinguish between them. And we use machine learning, such as, for example, SVM support vector machine. And then we send the command via TCP/IP protocol from Osaka city to Kyoto city. And this is like the decoding accuracy. So we achieve like 70%. 70% in BMI, in motor imagery, especially in motor imagery, because some people are, for example, using P300 SSVP. This is a different modality. they can reach 100% or 90%. But in the motor imagery, it's still difficult. And this one, it was like a new paradigm to like distinguish between bilateral movement. So that's why the accuracy is still around 70%, which is like acceptable to go for real-time application. And then after like analyzing and understanding what is going on inside the brain, what our goal was like to do some like engineering application to control this human-like robot bilateral hand to do any like daily life tasks. Okay, so this is like the flowchart for real-time decoding. And you can see here the real-time, sorry, so you can see here, I will just make it maybe. So you can see here, this is the human-like robot. This one was in Kyoto City, and this subject, this patient was in Osaka City. And he's like moving his bilateral hand. I'm not sure if you can see here his hand. And then the robot is doing almost the same things in real time. It was like very high speed. So this is the idea, but our goal, it was not this one. So now, okay, we understand what is going on when someone moves his bilateral hand, and we succeed like to control a human-like robot, both hands. So our goal was always to control the third arm. So this one also was in ATR. I was like in collaboration with Ishiguro professor and also Nishu professor. So they realized this mind control robotic for the third arm. Okay, they use EEG signals, but to be honest with you, okay, I'll be honest with you. When you use EEG equipment, there is a lot of like muscles activity contaminated. So we are not sure exactly if these people are using their real brain signals. Maybe there is a huge like muscles activity coming from, someone is typing or moving. So that's why we want to do almost the same experiment, but using the MEG equipment. When we use MEG equipment, we are like likely to like avoid the muscles activity. So you can see here the subject, he has to play here. There is a ball inside and he is playing, and there is like the third arm. And we are asking the subject to imagine, like kind of oriented goal, to imagine that this hand, it's his one part of his hand, and he is like trying to grasp that bottle. And we are still, to be honest, we are still analyzing this data and see which area inside the brain is responsible to control the third arm. We know which area is responsible like to control bilateral hand movement around sensory motor area, but we don't really know what is going on when someone imagines that this is his hand and he wants to control it. And this work was like in the cover page of this journal, IEEE Transaction. So your goal may be to make a robot and think about the interaction between human and robot. But our goal is to make a human more strong, because we do believe that we are not strong enough. So we don't have like more abilities, and that's our goal. So we want to combine the human with the robot. So that's the future perspective of this maybe BMI in the future. So we want you to get more arms, and like that you will be able to do many tasks in like few minutes. Thank you very much.
Thank you a lot. One quick question, just one.
Thank you. Thank you so much for the great presentation. I have one question. You design real movements and motor imagery.
Yes,
so
all of them.
I think participants may move actively. So how can you control participants' behavior? I mean, sometimes participants move very quickly, but some participants move very slowly. So how can you measure participants' behavior, and how can you control this movement?
Yes, that's very like scientific question. So the behavior of the patient to move his hand, to grasp, we just ask them to move their hand as natural as always, to just avoid many things in the brain. Because if someone is moving fast or like very slow, of course it's like the amplitude, it will be different. So we just ask them to grasp as natural as usual, I mean. Yeah, thank you. But we didn't take this one into consideration.
I was discussing.
Okay, thank you.
Okay, thank you very much.
Thank you.
I invite